We present Lemon, localized editing with mesh optimization and neural shaders, an editing method that deforms polygonal meshes based on given text instructions while preserving geometric consistency. As deep learning techniques gain prominence in both computer vision and graphics, neural rendering plays an important role in 3D reconstruction. Neural radiance fields, NeRFs, and Gaussian splatting are advanced volumetric scene representation techniques, with NeRFs using a continuous volumetric function and Gaussian splatting leveraging a collection of Gaussian kernels, both enabling high-quality novel view synthesis. Neural deferred shading, on the other hand, jointly optimizes the mesh and shader, achieving accurate and efficient reconstructions. Recent advances in diffusion models offer image generation from text or other conditioning data. Instruct Pix2Pix enables text-guided editing of existing images, while ControlNet addresses challenges in text-to-image models by incorporating spatial conditioning, like normal maps, to preserve geometric details. Instruct NeRF to NeRF introduced a text-based editing approach for NeRF scenes by leveraging an image-conditioned diffusion model to generate new images based on a scene's NeRF and its original input images. These generated images iteratively update the training dataset, guiding the NeRF to converge toward the desired edits. Similarly, Gaussian Editor extended this concept to Gaussian splatting, enabling text-driven modifications to Gaussian representations for novel view synthesis. Despite their innovation, these techniques rely on implicit representations, which limit their ability to directly manipulate surface geometry, making them unsuitable for precise polygonal mesh editing. For tasks requiring accurate mesh reconstruction, additional pipelines are needed to convert these representations into 3D meshes. We propose Lemon, a fast and efficient method for localized mesh editing. We identify important vertices and apply ControlNet using normal maps and shaded images during reconstruction based on text instructions. We localize modifications and iteratively update the multi-view image dataset with modified pictures, allowing us to quickly deform the mesh to align with the instructions while preserving its original structure. For pre-processing, we gather multi-view images, an initial mesh and a text instruction. We gather segmentation scores for each view based on text instruction using ClipSeg. Afterward, we project segmentation scores onto the initial mesh and aggregate them to calculate vertex scores. Finally, we backproject these scores to obtain image scores. For our editing pipeline, we utilize all the inputs and outputs obtained during the pre-processing step. In each iteration, the mesh is rasterized from input views, and geometry buffers with per pixel positions, normals, and masks are generated. The geometry buffers are processed by a neural shader to render a color image for the given view. The rendered images and normal maps are used as conditioning for ControlNet to generate modified images based on the given text instruction and input image. We mask the important parts of the generated image and combine it with the input image to create the updated image reflecting the changes. We compute the difference between the rendered and updated images using an appearance loss, guiding the parameters toward the desired edit. We update the mesh's vertex positions and the neural shader's parameters using gradient descent to achieve the intended modifications. We compute a mask loss to align the rendered masks with the image scores, and we apply regularization to the mesh to promote smoothness and prevent degenerate vertex configurations during our editing. We mask important regions based on our vertex scores, updating only the relevant vertices during editing to maintain localized modifications. In the end, we obtain an edited mesh where only the relevant regions have been modified according to the given text instructions. We evaluate our method on the DTU multi-view dataset to demonstrate its mesh editing capabilities. We compare our method with Instruct NeRF to NeRF and Gaussian Editor, using the surface extraction techniques outlined below to extract meshes from these methods. Due to their decoupled processes, these approaches often produce discontinuous meshes, whereas our method generates fine-grained meshes that align closely with the given editing instructions. Our neural shader also produces adequate rendered images with geometric consistency across views, demonstrating that our method can adapt to significant structural changes while preserving the object's geometric and shading characteristics. We use clip directional similarity and a user study to evaluate how well edits align with prompts. Our method outperforms others in this metric, demonstrating its ability to follow edit instructions more effectively. Unlike other methods that rely on decoupled processes, our approach integrates mesh extraction and neural shading, enabling faster and more efficient mesh and view synthesis while maintaining a strong balance between quality and speed. Thank you for watching.